Welcome back everyone. Till the last lecture we were looking into state space modeling of a system. We took systems and found out the state space of those systems, which means we wrote down the differential equations of the system in the form x dot equal to ax plus bu. Today what we will see is how are the state space related to the transfer functions of the system. Let us dive into that now. So, the first question that we are asking is, if we are given the transfer function of a system, can I write down the state space of that system? So, suppose you have a general nth order linear differential equation with constant coefficients given as here. Here we are considering that m is less than n, and you know the reason for that because we are always considering causal systems in this course. Of course, m can also be equal to n, but here we are taking m to be less than n, and I will generalize it to the case when m equal to n soon. Now, in order to find out the transfer function, you by now know what to do. You have to take the Laplace transform on both sides considering initial conditions to be 0, and this is the transfer function that we will get. Now, we want to find out a state space of the form x dot equal to ax plus bu and y equal to cx plus du from this transfer function. Now, how to do that? So, the trick is, first we will write down the transfer function in this form, where we will write down gs as x1 by u into y by x1, x1 being a new variable that I am introducing, and I call x1 by u to be 1 by the denominator of the transfer function and y by x1 to be the numerator of the transfer function. So, now what we will do is we will only look at this part first and then we will come to this part. So, let us try to write down the state space equation corresponding to this, and you will see that once I write down the state space equation corresponding to this, it will be very easy to write down the output equation or y equal to cx plus du using the state space information equation that we have found out and this expression. So, I will take these two parts separately. So, let us go for x1 by u first. So, x1 by u is given by this form, and here again I am trying to write down a state space equation for this transfer function say. So, what are the first step? If you have to model a system, you have to write down the state space equation. What are the things that you should know? First, you should know the input and output, and since you are writing a state space equation, you should know what the states are. How are you defining the states? So, in this expression you already know what the input and output is. So, the input here is us and the output is x1. So, now we will define the states, and the states will be defined as in this form. So, we will take the first state to be the Laplace inverse of x1s, which is nothing but x1t. Remember, this is a variable that we have introduced. Okay. So, x1t here is defined as the Laplace inverse of x1s. Then we define x2 as x1 dot, x3 as x2 dot, and so on till xn, and using these variables I define the state vector. Okay. So, what we have done, again this we are doing, we are creating a variable that does not have any physical interpretation as such. Okay. So, we have created a new variable, the new variable is x1s, and the first state is defined as Laplace inverse of x1s here, and then the next states are x2, x3 and xn are just derivatives of the previous variable. So, for example, x2 is x1 dot, x3 is x2 dot, xn is xn minus 1 dot. and you can see that I have defined n state variables. Now I take all these n state variables together and make a state vector, and this is the state vector that we have. So once we have the state vector, now we will try to write down the state equation. So the state equation will be of this form, right, because x dot must be equal to Ax plus Bu. So this is what we are expecting the state equation should look like, and notice that now we can easily write down the state equation, because what is the first state equation here, what is the first differential equation here? In the left hand side, the first equation is x1 dot, and I know that x1 dot here is nothing but x2, which means if I have to find out x2 here, so I have to have a 0 1 0 dot 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 0 0, because when this vector multiplies with this vector I get x2, and what will be here, I can put 0 here. So you see the left hand side is x1 dot and the right hand side is x2, and I know that x1 dot equal to x2. So this will be my first equation in the, or the first state equation. So I think you should now understand what will be the second equation. The second equation is 0 0 1, and rest of it will be 0, because x2 dot is equal to x3, and so on. I can keep on doing this till xn minus 1t, because xn minus 1t is equal to xn minus 2 whole of t dot, right. So we can actually go ahead and write xn minus 1 dot is equal to xn t, right, and that is the equation that we are writing here. So the second last equation is, on the left hand side we have xn minus 1 dot, and you can see xn minus 1 dot is nothing but xn. So we can write down the second last equation in this way. Now comes the last equation. So now in the last equation, the left hand side has xn dot here, and the right hand side here will have to be some row vector that I will have to put here, okay, and that must multiply with this xt, plus here something will come multiplied by ut. So I have to find out this differential equation, because this directly cannot be found out from these definitions. So we go back to the transfer function 1 by the denominator of the actual transfer function. So here you can see that us will come out to be this, and then I can rewrite this equation as s to the power of n x1 as equal to this. I am just rewriting the equations. I have just kept s to the power of n x1 in one side and taken the rest to the left. Now what is this? Notice this is minus a naught x1s plus a1 s of x1s, but what is s of x1s? S of x1s is, you see, if I take a Laplace transform here, s of x1s is nothing but x2. So this is nothing but a1 of x2s, similarly it will be a2 of x3s, and if I keep on continuing, at the end we will have an minus 1 x of s whole plus us. And so you can directly see, if I write down the, if I again take Laplace inverse here, so s to the power of n x1 s is nothing but x n dot t. So s, and on the right you have a naught x1 t plus or minus a1 x2 t minus a2 x3 t minus an minus 1 xn t plus ut. So I can directly look at this differential equation and write down the last row something like this. Notice the good thing about this is the last row can directly be read off from the denominator of the transfer function. Okay. So the coefficients, if you see, this is a naught, so here it is minus a naught, then a1, here it is minus a1, and so on. So directly by looking at the coefficients I can write down the last row. So this is the state equation corresponding to this part. Now once I know the state equation, I can directly go ahead and write down the output equation as well, because what was ys by x1s? It was the numerator of the actual transfer function, and this can be written as ys can be written as this. Notice, and this is nothing but yt equal to b naught x1 t plus s of x1 s is nothing but x dot t. So, this is nothing but x of 2 t, because I know that x1 dot is equal to x2. Then similarly, you can go ahead, if I rewrite this equation. So, this equation will become something like this. So, this equation will become y of t will be equal to b naught x1 t plus s of x1 is nothing but x2. So, b1 x2 t plus dot 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 bm minus 1 x of m t bm x of m plus 1 t and so on. So, this is the expression that we will get, and once we have this expression, your y will come out to be something like this. We can write down yt as this. Notice one important thing, I have taken m to be less than n, which means somewhere down the line here at some point, suppose this is x of m t dot dot. So, there will be a bm minus 1 term there, and after that rest of the terms will become 0, right, because those terms do not appear in this equation since m is less than n. Of course, if m is equal to n, then all the terms will show up. Okay. So, the takeaway is that if you are given the transfer function of the system which is of this form, for of course, in this case you have taken m less than n, then just by looking at the transfer function you can write down the state equations, because now the state equations can be written down in this form, where the last row here comes from the coefficients of the denominator and the matrix here comes from the coefficients of the numerator. Of course, now I have to generalize it for the case of m equal to n, and I will generalize it for m equal to n. Now, notice, if suppose m is equal to n, the numerator and the denominator have the same degree, which means I can divide the numerator by the denominator. So, for example, if you have s plus 1 by s plus 2, I can go ahead and divide s plus 1, so that I can rewrite this equation in this form, that s plus 1 by s plus 2 can be rewritten as 1 minus 1 by s plus 2. And now you notice that this is again a strictly proper transfer function. The numerator degree is 1 less than the denominator degree, and this is a constant that you will get, and that is what we are writing here. So, in a general form we are writing it. So, if the numerator and the denominators are equal, then I can always divide and get a constant out, and then write the rest as a strictly proper transfer function. Now, once I have this strictly proper transfer function, I know what will be the state space for this. The state space representation for this can be of this form, where I will write down the A matrix in this form, where the last row of the A matrix comes from the denominator's coefficients, then B becomes 0 0 0 0 1, and then the C matrix here comes from the numerator's coefficients, which is beta naught, beta 1 and all. You continue this, and finally there is this extra term, because of this d there is an extra term called plus dut. Okay, because this why does this happen? Why is it adding up and it will work? Because you see, if you look at ys from this expression, if I call this part, say let me call this gs. So, y not gs, let me call this say ms. Okay. So, ys is nothing but d into us plus ms us. Now, for ms us I know already how to find out the state space equation, I have already found it out, and then just I have to add d of us. So, in the time domain this becomes yt equal to d of ut plus the expression that will come due to the strictly proper case. So, this was sort of the derivation by which we can get to the solution, but what is the main takeaway is that if you are given a transfer function, then you can directly write down a state space equation for the system just by looking at the coefficients of the denominator and the numerator. Okay. And the expressions will look, A, B, C, D matrices will look like the one that I have just now shown. Now, this states that we had chosen, remember when you are writing, again when you are writing the state equations, you will have to first define the state variables and the state vector. In this case, we have defined the state variables as, the first state variable as Laplace inverse of x1s, and then x2 was x1 dot, x3 was x2 dot, and so on. This collection of state variables, is called phase variables. Okay. This has been given special name because you get a special form out of the state equations. So, these are called phase variables. So, and this form in which you are writing the ABCD matrices is also called phase variable form. Okay. So, let me take this example that we had done previously. If you look at this RLC circuit, we can find out the state space equation of this circuit in this form, and now I will just put some values there in place of R1, R2, C1, C2 and L. So, the state space equation would look like this. Now, this is the state space equation when you chose the states to be inductor current and capacitor voltages. Now, instead of doing that, I can also write down a state equation without choosing inductor current and capacitor voltages as the states. Instead of that, I can actually directly write down the phase variable canonical form for this system. So, for that I can find out the transfer function of the system. So, to find out the transfer function of the system, I have converted this electrical circuit to its Laplace domain. So, how do you do that? So, this resistor becomes 2, this inductor is SL, the impedance is SL. So, this becomes S, this is a 2 ohm resistor. So, it is 2. So, this is a 0.5 farad capacitor. So, this is 1 by SC, C is 0.5. So, 1 by 0.5 S, and here it is 1 by S, C here is 1. So, this is 1 by S. So, once I have converted this, all these terms have become impedances now, and then I can directly write down nodal equations for this circuit. So, the nodal equations will be, we will try to write down the nodal equation at these points. Remember again, what are we trying to do? What I am trying to show you is that you can find out state equations, state space equations, state equation and the output equation of a system directly by using state variables which have physical meaning, or you can also find out state equation of a system by mathematically without even bringing into physical meaning into the state variables. So, for that what I am showing is I am trying to find out the transfer function of the example that is given to you. Of course, you know that when you have to find out transfer function, you need to identify the input and the output first, but since the state equations were already written, so I know that the input is Vt, the output is Vc2. So, the transfer function that we are looking for is Vc2s by Vs. This is the transfer function we are trying to find out, and that is the reason I am writing down the KCL at these points, at these nodes. So, if I write down the KCLs, you will see that Vc1 minus Vs divided by S plus 2 plus Vc1 by 1 by S plus Vc1 by 2, Vc1 minus Vc2 by 2 is the first equation that you get, and the second equation that you get is Vc2 divided by 1 by 0.5 S plus Vc2 minus Vc1 by 2. This is the second equation that you get, and from here if you keep on eliminating all the variables and keeping just Vc2 and V, you can come up with the transfer function of the system to be this. So, this is the transfer function of the system. Now, once I have the transfer function of the system, I can directly write down the phase variable canonical form of the system, or the state equations and output equation of the system, considering the states to be phase variables. Okay. So, how do we write that? Now, notice that this is the transfer function of the system, and look at the standard transfer function. In the standard transfer function, in the denominator you can see that the highest degree had coefficient 1. Here our highest degree was not coefficient 1. So, we first make the highest degree coefficient 1. So, this is the transfer function where you can see that the highest degree has coefficient 1. Now, once you have that, you can understand, you can directly see that this is your alpha naught, this is your alpha 1, this is your alpha 2, and this is your beta naught, beta 1 is 0 here, beta 2 is 0 here. So, we can use these ideas to get to the final state equation of the system. So, this will be the state equation of the system. There is no D here, you cannot see a D here. Why? Because you see the transfer function to start off with was a strictly proper transfer function, and for strictly proper transfer function you do not have to divide and get the constant out, that is why you do not get a D here. So, you can directly see here that if you have a transfer function which is biproper, that means the numerator degree and the denominator degree are equal, then only you will get a D term, otherwise the D term will not be there. If it is strictly proper, that means that the numerator's degree is less than the denominator's degree, you will not get the D term. Okay. And the other thing is that both these state equations, this is also a state equation of this RLC circuit, this is also a state equation of this RLC circuit, both of them represents the same system. Okay. So, only difference is that the state equations that we have taken are have different state variables, and that is the reason they look different. Okay. But they are related, they have a relation between them which we will look at later. Okay. So, with this I end this lecture today, and then in the next lecture we will see how to get the transfer function from the state equations. Thank you.